Continuing with the discussion of the periodic table, we now want to talk a little more explicitly about the organization and kind of the labeling of elements on that table. So when we're talking about the periodic table, it is very much so a table, and we're going to have names for the rows and columns. Rows are going to be called periods. If you remember, the whole point of periodic table was that you have these repeating patterns that follow a period. So each row in the table is going to be then kind of one time through the period. So you would expect each element in a given row has unique properties. And the periods are going to be numbered just from top to bottom. So the first row is period 1, then period 2, so on and so on. The columns are then called groups. Oftentimes, you'll also hear them called families. So groups or families. Groups is more the technical term. Families is a little more historical, but it sticks around. The elements in a group have the same chemical properties, right? Each row is one time through the period. So whenever or one time through the pattern. So every column then is that similar kind of that point in the pattern. And so elements in a group have similar chemical properties. We would expect them to do similar chemical reactions, to behave in similar ways, to form similar compounds in similar ways. The groups are also numbered from left to right, going up 1, 2. There's also letters involved. So we're going to use 1A, 2A stuff. You'll poke around. There's some different numberings for groups. Some that just use numbers, some that use numbers and letters. Different types of those organizations. We're going to generally stick with one that is using 1A and A's. Whatever you're using, it's fine. But we can kind of stick with that idea. We want to be using, whenever I ask a question, I'll give you a periodic table that I'm talking about. And I want you to use that periodic table that has those labels on there. So you can see here is again a table with the explicit numbering. You will kind of just pick up on the periods, especially because they're just counting rows 1, 2, 3, 4, 5, 6, 7, but you can always use those. One kind of nuance with that, you'll note that 1 does always start up here. So like, for example, anything that's not on the edge, there is nothing in period 1 in the second column. Down here, if we looked at, say, chromium, Cr, that is in period 4 still. There just is nothing above it, above chromium in the earlier periods. That column starts with period 4. And then when we look at the numbers of the groups, you can see there is like the 1A, and then there's also that number in parentheses. We're going to use the 1A, and if you'll note the A's, remember we talked about the main group, that's where we find 1A, 2A, and then it's kind of hard to see, but that's 3A, 4A, 5A, 6, 7, 8A. And we're going to use that designation. And so the transition metals are then where the B's show up. So the B's are showing up down in the transition metals. So 1B, 2B, that sort of kind of progression. Generally, we're not going to really be too concerned about the group numbers of the transition metals. Again, the main group gets that name main for a reason. We're going to do a lot more chemistry with those guys. So we want to get some practice working through that idea. What element is found in group 4A and period 3, and what metals are in group 6A? Okay, so when we're working through this, we want to get, kind of put this together, the organization of atoms in the table. So starting out, what element is found in group 4A and period 3? We're going to be thinking group is a column. So we see 4A, we're told it's 4A. We want to look and find where 4A is, which column that's talking about. So everything in that column is in group 4A. So carbon, silicon, germanium, tin, lead, and then whatever FL stands for. So but those symbols are right there. And then period 3, we can look over here. We can see period is the row, so we're looking at the third row. We can trace those together and find that it is Si. So Si would be a fine answer. If you called it silicon or you knew that, that's fine as well. But you could also just say Si because that means it's silicon. One of the things we do want to be careful of is you'll note a lot of times when we see period 3, you have a tendency to want to count down, like 1, 2, 3, and then call it germanium. But we do want to note that period 3 isn't just 3 from the top, because you can't forget that period 1 up here just has nothing. There is no element in group 4A and period 1. That just doesn't exist. Okay, so what metals are in group 6A? So group 6A, we know again, when we see that A or B, if there's a letter involved, that means you're talking about a group. That's a column. So we know we found that group. Our metals, we know in this case, there is this divider between metals and non-metals. It is that staircase. So the question is, which side are we on? And metals are to the left and below. Okay, so the left and below. So that's where it's going to be still in group 6A. The metals are going to be PO and LV. Okay, so PO and LV, I think that's polonium and livermorium. Those are, not that when you get that far in the periodic table, we're not really doing a ton of chemistry with those things. Those are pretty dangerous. And so, but those we can still define, those are the metals in that group. So those metals have similar chemical properties with, say, oxygen. They have different physical properties, but their chemical properties are the same. Everything in group A is doing similar chemistry. So we have those kind of systematic numbers, those ideas of having group 1A, 2A, 3A, these periods. Those are based around the idea of everybody trying to come up with a common language, a more modern common language that we can all use. Historically, a lot of groups just had special names, and those special names came from, but they predate the periodic table. It was people just kind of doing experiments of finding elements that had similar properties and grouping them all together. So historically, every single column had a common name. Now, only the ones on the edges of the periodic table have stuck around. So the first column is the alkali metals. The second column is the alkaline earth metals. Those are pretty similar names. And on the other end of the periodic table, we have the halogens and the noble gases. So we have kind of the extreme sides of the periodic table where we have some really unique and important types of reactivity, and those names have stuck around and we still use those. So we do want to get comfortable with those. You don't need to know group 5A, so like that nitrogen group. You don't need to know that that's called the pnictogens because no one really uses that anymore. Halogen, you've probably heard halogens out in everyday life, halogen light bulbs, halogen lamps, those sorts of things where those come up. So those names still have stuck around. So first column in the periodic table is the alkali metals, the very first column on the left of the periodic table. These are defined, they're all metals, as the name implies. They are all very soft. So for example, this person is cutting potassium with a handsaw. That's really uncommon for metals. If you think of like iron, you can't just cut it with a handsaw. This is also like a pretty big chunk of potassium that this person is cutting. Very relatively soft. They are also importantly extremely reactive. Any of these metals, when you put them in water, here you can see an example, when they get in water, they create a lot of hydrogen gas and so much heat that they then also, the hydrogen gas they create spontaneously lights on fire just from all the heat produced from the reaction. So, really, really aggressive reactions with water, really, really highly reactive. That's one of the reasons why their name has stuck around, because you can do a lot of chemistry with these things. But they are still all metals. They have all the properties of metals. They're just additionally very, very soft and very, very reactive. The other side of the table, second to last column, are the halogens. And the halogens also are very, very reactive. They are the unique column in the table. At room temperature, you have solids, liquids, and gases. Fluorine and chlorine are gases. Bromine is a liquid, and then iodine and acetine are solids. So you have every phase of matter represented in the column. They are also characterized by extremely high levels of reactivity. In their elemental form, they're extremely dangerous. And things like halogen lamps and other applications, they're in compounds that they're reacted with other elements. But chlorine is used to, say, kill things. So we use it to disinfect pools because it kills things in those pools, right? It kills the living things that are in those pools, and that's how you disinfect it. When it comes to, you can't use it on a human because it would kill disinfect the things inside the human and kill those things. So really, really dangerous in their elemental form. They're very, very reactive. And so we do use them for those. You can do a lot of chemistry with them. That's, again, why the name has stuck around. Last thing we talk about is the noble gases. This is the very last column on the right of the periodic table. These are also characterized by reactivity, but it's the lowest reactivity. These are all gases. So helium, neon, argon, krypton, and xenon are all gases at room temperature. They don't do really any chemistry. Argon, krypton, and xenon, you can get kind of crazy and do a little bit of chemistry with them, but for the most part, these things really don't undergo chemical reactions. And while that's not useful if you want to make new compounds with new properties, this has its own unique purposes. So, for example, blimps, balloons, we use helium in those because it's a really low density gas. It floats, and importantly, it's not reactive, so it won't light on fire. Old incandescent light bulbs, which still are around in a decent number of rooms, use argon, right? The gas inside of those is argon because you light it up by running electrical current through a metal and just getting it really, really hot. If there was oxygen, if there was air in there, it would light on fire. But because you fill it with these non-reactive gases, they don't light on fire. So they don't do chemistry. So these are really, really useful in instances where you don't want a chemical reaction to happen. You can use these gases. So like saying a blimp, you don't want it to light on fire because that would really limit its ability as a blimp. So we want to keep it non-reactive. We use noble gases for those purposes.